Well, we're not just going to find the eigenvalues. I think it should be a great idea to find the eigenvectors.
I sincerely hope so.
And yes, that will be what we will do. So, find the eigenvector associated with lambda equals 4. And so what we do, we say we'll put lambda equals 4 back into our system and say that times k1, k2, k3 has to come out to be the 0 vector. So 1 minus 4, that's 1 minus lambda. 1 minus 4, that's 1 minus lambda. See, I'm going back to this matrix and subtracting 4, the eigenvalue of 4 from the main diagonal. So there we have it. We have negative 3, negative 1, negative 1, 0, negative 3, 3, 0, 3, negative 3 times this vector, and it comes out to be 0. So let's do some row operations. I was thinking negative on this matrix, this expanded matrix. This one is a 3-row, 4-column matrix, but the last column is all zeros because I'm trying to solve this equation. So I'm using the augmented matrix to solve this system of equations. So do negative a third times row 1, that makes that a 1, this a 1/3, this a 1/3, say 1, 1/3, 1/3, and 0 stays the same. And then we're going to do negative 1/3 times row 2, so 0, 1, negative 1, 0, 1, negative 1, 0. And now we're going to do some row operations. We're going to say negative 3 times row 2, add to row 3, and negative 1/3 times row 2, add to row 1. And when we do that, see, negative 3 row 2, add to this, negative 3 this, add to this, 0, negative 3 add to this, 0, negative 3 add to this, 0. So, and then we're going to do negative a third this, add to this, so 0 here, negative a third this, add to this, so we got 2/3 there. And so now we have a system of equations that has an infinite number of solutions, but we expected that. So the bottom row is all zeros, and therefore if we let k3 be arbitrary, row 2 says that k2 minus k3 equals 0, so k2 equals k3. Row 1 says k1 plus 2/3 k3 equals 0, so k1 equals negative 2/3 k3. And so we have an eigenvector, negative 2/3 k3, 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 and if we factor out the k3, because that's just going to be a constant anyway, and that would be absorbed by the c in our solution, right, when we eventually write it. So this eigenvector is negative 2/3, 1, 1. Although you can make a good case for calling it negative 2, 3, and 3, because any constant multiple of an eigenvector is also an eigenvector.
Oh, boy!
Yeah, okay, that's kind of nice. So, so examples 2 and 3, find all the rest of the eigenvectors for this system. All right, we'll do that in the next video.